Hello there, math fans. Dr. Andy Lovelace. One last thing about curvature before I put this to bed and move on to other things. Curvature comes up when we talk about transitions between curves, because it's one thing you might want to measure if you're traveling along a curve. We used to have a worksheet where we would do this in our Calculus 3 course, but that's long since not been used. But it reminded me of this. So if you go out and look, like I found a picture of the Seattle skyline here, there are loops, circular loops, but the roads that go into them are not circular. You can see that. There's these transitions. You don't like to change from straight to circular. And here I have an example here on the right. You can see it. So if I move here and I'm going straight, the curvature is 0. If you then still 0, still 0, still 0, then the moment you get on the circle, you now have a constant curvature. In this case, I think the curvature is like a fifth or something. So that's a big shift that if you were actually in the car or on a train, you would feel that as a sudden jerk. That doesn't mean sometimes roads aren't designed that way, but it's something we have to consider. Now, the first roller coaster ever built, this is kind of a famous roller coaster, they used a circle. So they went basically from a straight to a circle. And there were two riders, like you can even see like a video. But they said that when people hit that turn, they had 12 G's of force on them. And all sorts of people had whiplash, hurt their backs, hurt their necks. That was the first roller coaster. After that didn't last very long. But that was an interesting story I didn't realize. After that, they started making this so-called kind of teardrop form. But it's these transitions. You can't go straight. You can't go from something that's curvature 0 to something with dramatic curvature. So we need a transition to build into that curvature. All right. So the same is true for train tracks. You can't have the train. So there's this whole theory you can look up. Like I just looked at a general like road and track design page, and I saw that it basically said here's the transitions we use, here's the rules for that. I was thinking about when I would build train tracks with my son. I think these all were parts of a circle. So we did not have transition pieces. I did read that the first train tracks ever built did go straight from lines to circles, but the trains were going so slow it didn't matter. So what do? They need to transition curvature. They need to transition from 0 curvature to some other curvature. These are these so-called transition curves. Okay, so the comment I wanted to make is there's quite a history of this. People have studied curvature for a long time. Bernoulli posed a problem like this in the early 1700s. As often is the case, Euler solved it, and then this thing became called an Euler spiral. Then it was rediscovered by this somebody studying, what did they say? Optics, not optics. A physicist, Fresnel, and it led to these Fresnel integrals, which my students are going to be mad about because I always mention these as integrals we can use Taylor series for. Now I know a bit more about where they come up. And then the late said something like 1880, this Arthur Talbot, was actually designing a train track and figured the same thing out. So sort of rediscovered twice. There were other people that studied it in between. One scientist or one person whose last name was Cornu, so sometimes they're called Cornu spirals. And then later someone named it a clothoid. Clothoid derives from the word spin, like spinning wool. So anyways, that's the story. If you look on Wikipedia, you see this little picture of it, this transition. What I'm going to do here is show you the formula, show you why the Fresnel integrals give you this, and then show you some visuals. but you can find other things on it. If you want to avoid that transition, you have to do something in between. So I made a second function here that I'll show you here, and let me graph it. So you have some sort of transition. Now, how you do that, that's the actual, modeling, and that's for the engineer. But it's more gradual. It gets slowly changes instead of dramatically. Then eventually gets to where it matches up. Okay, so what Euler did was he discovered a curve whose curvature gradually changes from 0. That's the so-called Euler spiral, and it looks like this. So as you move, it gets proportionally more curvy. So gradually it curves. So the curvature's 1, and then 2, and then 3, and then 4. The curvature then gets really fast, and this is the curve you get. So if I animate it, it will... Oops, I'm going backwards. Let's go forwards in time. But the point is, if you then match a circle to it, if I give you those osculating circles, which look like this, and I'll show you this in a moment. Let's come back. So once you get to, right now we're at 1, the radius of that circle is 1. I go a little further, the radius of that circle is a half. I go another half a second, or another second, let's say. The radius of that circle is a fourth. So it goes in a gradual way, and it leads to this spiral. So basically you say, I'm going to make a curve that gradually turns so that the curvature goes gradually up. This is it. And so we use segments of that for transitions between various things we want. So we take whatever curvature we're starting at to whatever curvature we want to end at. We take a piece of the Euler spiral because it gradually changes. So that's kind of interesting and fun to watch. There we go. Okay, let's finish this up with just a little discussion of this. So I was like, well, we got to be able to show that, right? So I grabbed the Fresnel integrals. I pretend that was a curve. You can see that it's defined in terms of an integral because we don't know how to nicely compute that integral except with Taylor series. In fact, a lot of the methods for using this would involve some sort of Taylor series approximation to design our track. Okay, so anyways, but we still can use the formula. So if you don't remember from the previous videos, the formula for curvature is this. This is what we want to study. And Euler figured out that this would have curvature that's linear. That's a linear function of t. So we just need to start computing some derivatives, plug in, see what we get. So let's play that game. So here we go. I'm going to write this as a vector function so we can match up with our formula. And I already did this. So there's the function using those pieces. The first derivative is a chance to use the fundamental theorem of calculus part 1. So that's kind of exciting. There's the derivative. The magnitude of that, notice it's 1, so that does simplify. Here, let me make this a little bigger. And then the second derivative, you got to do a little chain rule piece. And then lastly, let's grab this, make this a little bigger. So lastly, I did the cross product. Cross product actually simplifies because you get a sine squared plus cosine squared, so you get a -2. You do the absolute value, and to get the curvature is 2t. And so when t is 1, the curvature is 2. When t is 2, the curvature is 4. It's a linear function. That's kind of interesting. So anyways, I just thought that's trying to give a little more depth. Students are always asking me about what is this curvature about. Again, this is not essential for the course, but might give you some more depth, might make it more interesting. All right, thanks for listening.